Chapter 14, Acids and Bases. Our outline is acids and bases, Ka and Kb, conjugate acid-base pairs, Kw, pH, pOH, pKw, pKa, pKb, pH of weak acids, pH of strong and weak bases, polyprotic acids, and pH of salts. Acids and bases. Acids and bases are a very important class of compounds. Many natural substances are acids, with fewer being bases. pH you've probably heard of in connection with acids and bases. pH depends on the particular acid or base and on its concentration. The pH scale at room temperature varies usually from 0 to 14, but it can go below 0, it can go above 14. At around room temperature, a pH of 7 means we have a neutral solution. The H plus ion concentration equals the OH minus ion concentration. When the pH is less than 7, we have an acidic solution. The H plus concentration is greater than the OH minus concentration. When we have a pH greater than 7, we have a basic solution. The OH minus concentration is greater than the H plus concentration. A basic solution is like an acidic solution, corrosive, reactive, hard on our skin, etc. Here is a picture of some hydrangeas. Apparently, depending on the pH of the soil, they're either blue or pink. Many foods are acidic. Here's a bowl of tomatoes, citrus, grape, and those are acidic. We have a pH scale on the left which shows at various pH values common substances and their pH values. The table on the right shows specific substances and their typical pHs. Stomach acid, which is HCl, varies from a pH of 1 to 3 depending on what we've eaten, how recently we've eaten. Limes, lemons, those are pretty acidic, as you probably know. If you've ever cut up a lot of lemons and not worn gloves, you might feel it on your hands after a while. Soft drinks are also acidic due to their carbonic acid. We see other fruits are acidic. Wine is a bit acidic due to substances like tannic acid. Beer is acidic due to for the most part, the same reason as soft drinks, the CO2 making carbonic acid. Notice that rainwater is acidic. That's due to CO2 from the atmosphere getting into it and making it slightly acidic. In the lab, the water, distilled water even, is a bit acidic depending upon how long it's been sitting. Because of the CO2 in the atmosphere, it becomes acidic. We see very few food items are in the basic range. Human blood is a little bit basic. All right, some definitions. We have two definitions for acids and bases that we will work with. A Bronsted-Lowry acid that's the Bronsted-Lowry definition for an acid, is it is a proton donor. We could also say a Bronsted-Lowry acid is an H plus donor. Why is H plus called a proton? Well, think of H, the atom. In its nucleus, it only has a proton because ordinary hydrogen has only a proton. It has no neutrons. In its electron cloud, the atom has one electron. Well, if we take away that electron and therefore have H plus, it's simply a proton. That's why we refer to H plus often as a proton. So you know that HCl, hydrochloric acid, is an acid, and it is an acid because it donates that H plus. So when we put some HCl into water, the H plus goes to water, so the HCl is acting as an acid, and what water forms is what's called the hydronium ion, H3O plus, where instead of just floating around in water, H plus actually makes a covalent bond to water, giving us the hydronium ion. So technically, we don't have H plus alone in water. We have the hydronium ion, H3O plus. A Bronsted-Lowry base is a proton acceptor. So NH3 is a base. It will take a proton from water if we dissolve it in water, leaving behind OH minus, the hydroxide ion, and itself forming NH4 plus. This is a useful definition that we will often use in this chapter. Another more general acid-base definition is the Lewis acid-base definition. You will probably use that if you go on in chemistry. A Lewis acid is an electron pair acceptor. Now this time it's an acceptor. Last time it was a donor, but notice that it's not a proton we're talking about, it's an electron pair. So a Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. So let's look at the base first. Ammonia has on the nitrogen a pair of electrons. Well, that pair of electrons is donated to the H on water, and in that sense, it is following the Lewis acid base definition. When it donates that electron pair, it forms that covalent bond with H on water, giving us NH4 plus and OH minus. A Lewis acid is an electron pair acceptor, so the H of HCl accepts a pair of electrons from water to leave behind only Cl minus, and water becomes then H3O plus. Water, turns out, is not necessary for an acid-base reaction. Here's an example with ammonia gas combining with HCl gas. When they combine, notice we don't have any water around, we just have these as gases. They're both colorless gases. When they combine, that is, their gases combine, we get ammonium chloride as a solid, which forms a white cloud. And the HCl, or rather the NH3, that pair of electrons on the nitrogen, is being donated. It's acting as a Lewis base to the H and forming the NH4 plus and Cl minus. We can see that in this diagram. So in the bottles on the left, we have NH4OH, which is another way of writing NH3 in water, just NH3. So we have a container of that. Notice it's colorless, a colorless gas. It's got the lid on. We have a container of HCl. When we open them and allow their vapors to mingle, we get what's shown on the right side. We see that white ammonium chloride cloud. Here's another Lewis acid-base reaction where we have BF3 acting as the acid, and we have again ammonia, so the pair of electrons on the nitrogen makes a covalent bond with the boron, giving us the product, and that's an acid-base reaction. Our next section is Ka and Kb. We can represent a monoprotic acid, and to be monoprotic means it donates one H plus, mono 1, protic for that proton. So it donates one H plus as HA. We will find that we work with many different acids in this chapter and future ones for that matter. And if it's a monoprotic acid, it only has one H plus to donate, then it's very convenient to write it as HA. So let's put HA in water, and we get HA plus H2O, forming H3O plus A minus. The equilibrium expression for this reaction is going to be that H3O plus times A minus divided by HA. Notice we leave water out since it is a pure liquid. Ka we can call the acid dissociation constant. It's the equilibrium constant for that equilibrium. A for acid. We can represent a base as B, like ammonia. Let's put that in water. So we put the base in water, and acting as a base, it takes an H plus from water, forming HB plus and OH minus. The equilibrium expression for the reaction is Kb, because we're talking a base this time. Kb equals OH minus times HB plus divided by B. And whenever we have a reaction involving H3O plus, we could say that's a Ka kind of reaction. It's yielding H3O plus. When we have one that forms OH minus, that's a Kb reaction. It's forming OH minus. Strong acids and bases. An acid or base is strong if it fully ionizes in water, if the equilibrium lies far to the right, if the Ka, the Kb is very, very large, is basically infinity. HCl is a strong acid. If we take 100 HCl molecules, put them in water, we will get 100 H3O plus and 100 Cl minus ions. The reaction goes all the way to the right. HCl is fully ionized. It's a strong acid. The Ka is huge. It's basically infinity. Think about it. Ka is the products divided by the HCl concentration. If there's no HCl left, we have number over 0, we have infinity. Sodium hydroxide, NaOH, is also a strong one. It's a strong base. If we put that in water, we get OH minus and Na plus. If we take 100 units of NaOH, we end up with 100 OH minus and 100 Na plus. The Kb is huge, it's infinity. Common strong acids are sulfuric acid, H2SO4, hydrochloric acid, nitric acid, HNO3, hydrobromic acid, hydroiodic acid, and perchloric acid. There are 6 acids that are these common strong acids. I want you to know that list so that if an acid is not on that list, you know it's strong, it's not strong, therefore it must be a weak acid. And it will matter very much that we differentiate strong acids from weak acids as we go through this chapter. Common strong bases are sodium hydroxide, potassium hydroxide, other hydroxides as well. Weak acids and bases. An acid or base is weak if it only partially ionizes in water, if the equilibrium lies far to the left, far to the reactants. So acetic acid, HC2H3O2, is a weak acid. If we put that in water, like 100 molecules of it, we only get about one H3O plus and one C2H3O2 minus. And what that means for us is it only very partially ionizes. The equilibrium lies far to the HC2H3O2 side. Ka is very small. In fact, Ka is 1.8 times 10 to the minus 5. Ammonia, NH3, is a weak base. If we take 100 ammonia molecules and dissolve them in water, only about one of them forms OH minus and NH4 plus. It's only partially ionized. Kb is coincidentally also 1.8 times 10 to the minus 5. So those are examples of weak acid, weak base. So just once again, Ka and Kb values for strong acids and bases are huge. Ka and Kb values for weak acids and bases are numbers, and they are given in tables 14.2 for acids and 14.3 for bases. And here are those tables. Here's table 14.2, Ka values for some common monoprotic acids. And we see at the top of the list we have the HSO4 minus acid with its Ka value of 1.2 times 10 to the minus 2. The fact that we have a value for it that's a number value, that's not just the word huge or large, means it's a weak acid. Also, you know it's not on that list of 6. And going down the list of acids, we see that the Ka values are getting smaller. The smaller is the Ka value, the weaker is that weak acid. So phenol, the acid at the very bottom, is the weakest of the list. Here's table 14.3, Kb values for some common weak bases. So we have ammonia, methylamine, ethylamine, etc. Those are all involving nitrogen. Nitrogen, with its lone pair of electrons, is a very, very common weak base. We see the Kb values in our table. They're not in order like they were for the Ka values, but the smaller the Kb value, the weaker the weak base. So of our list of bases, aniline, with its Kb of 3.8 times 10 to the minus 10, is the weakest base. Notice that Ka, Kb are unitless, just as we learned in our last chapter for the typical equilibrium constant. Our next section is conjugate acid-base pairs. HCN is not on our list of 6 strong acids, so we know it must be a weak acid. And if we put that in water, we get a little bit of Cn minus and H3O plus to form. So the HCN is acting as an acid, donating a proton. Well, the Cn minus can combine to some extent with the H3O plus, going back the other direction. It's an equilibrium reaction. When Cn minus combines with H3O plus, it is acting as a base in accepting a proton. And that HCN and the CN minus have a relationship. They differ by H plus, and they are part of the equilibrium system together. They are what we chemists call a conjugate acid-base pair. A conjugate acid-base pair is two substances related by the donating and accepting of a proton, H plus. The conjugate base of an acid is the base that forms when the acid donates H plus. So HCN is the acid, CN minus is its conjugate base. So HCN acts as an acid, donates a proton, and what it forms is CN minus, its conjugate base. The weaker is the acid, the stronger is its conjugate base. So the less inclined an acid is to lose its H plus, the more inclined is its conjugate base to gain back that H plus, making it a bit of a stronger but weak base. The conjugate base of a weak acid is almost always a weak base. Okay, next we have an example. What is the conjugate base of H3PO4? So we write the reaction of H3PO4 plus water in equilibrium with H3O plus H2PO4 minus. That should be H2PO4 minus. Now, the H3PO4 is acting as the acid, and its base is H2PO3 minus, H2PO4 minus. That is to say, the conjugate base of H3PO4 is H2PO4 minus. Also, notice that while H3PO4 is acting as an acid, the H2O is acting as a base, taking the H plus, forming H3O plus. So the water is acting as a base in this case, and it is forming H3O plus. It turns out that the H2O and the H3O plus are also a conjugate acid-base pair. Okay, so as we see, this conjugate acid-base pair concept applies to bases as well. The conjugate acid of a base is the acid that forms when the base accepts H plus. The weaker the base, the stronger is its conjugate acid, but the conjugate acid of a weak base is almost always a weak acid. Okay, so here's an example. What is the conjugate acid of CH3NH2? So CH3NH2 plus H2O is in equilibrium with OH minus plus CH3NH3 plus. So the CH3NH2, the base, the original base, acting as a base, takes a proton from water to form CH3NH3. So that is its conjugate acid. So the conjugate acid of CH3NH2 is CH3NH3 plus. And since water in this case is giving up the proton, it's acting as an acid, and it's forming OH minus, which is its conjugate base. Here's a table of some summary of stuff we've talked about. So the Ka value for a strong acid is large, for a weak acid is small. It has some numerical value. And for a strong acid, the equilibrium lies far to the right, far to products, far to the H3O+. For a weak acid, it lies far to the left. We don't get much H3O+. We get enough to detect it with a pH meter as being a bit of an acidic solution, but we don't have much. For a strong acid, it essentially goes all the way to products. So all of the original HA is now H3O plus A minus. So the H3O or the H plus concentration is approximately equal to the original HA acid concentration in a strong acid. That is, if we have a bottle of 3 molar HCl, what that means is we really have no HCl, the molecule in the bottle. We have basically 3 molar H3O+, or we could say 3 molar H+, and 3 molar Cl-. For a weak acid, the H+ concentration is much, much less than the original acid concentration. So if we have a 3 molar solution of acetic acid, we have almost 3 molar acetic acid, the molecule in the bottle, and a very small amount of H+ or H3O+ in the bottle. Relative strengths. Using Ka values, arrange the following species in order of increasing strength as acids. Okay, Ka values. The bigger the Ka value, the stronger the acid. For HOCl, its Ka value is 3.5 times 10 to the minus 8. For HCN, its Ka value is 6.2 times 10 to the minus 10. We know that HCl is on that list of strong acids, so we know it's a strong acid. We know the other two are weak because we have numerical values for their Kas. So HCl, a strong acid. The other two are weak acids. HCl is the strongest of the three. Ka of HOCl is greater than that of HCN. So HOCl is a stronger acid than is HCN. So in order of increasing acid strength, we would have HCN less than HOCl less than HCl. Again, using Ka values, arrange the following species in order of increasing strength as bases. So to compare OCl minus and Cn minus as bases, well, we use Ka values. The stronger acid of the two has the weaker conjugate base. HOCl is a stronger acid than HCN, as we established above. So OCl minus would be a weaker base than Cn minus. The weakest base is that of HCl. So Cl minus is the weakest base. It doesn't want to take on an H+. So Cl minus, the weakest base. After that in strength, we have OCl minus, and then the strongest weak base is Cn minus. So just remember that both OCl minus and Cn minus are weak bases. Okay, just a little review. What is the conjugate base of HA? So when HA acts as an acid, it forms the base A minus. So those two are the conjugate acid base pair, HA and A minus. A minus is the conjugate base of HA. What is the conjugate acid of water? Okay, so that's water acting as a base. When it acts as a base, it loses it takes on a proton, so it forms H3O plus. So the conjugate acid of H2O is H3O plus. What is the conjugate acid of ammonia? So that's ammonia acting as a base, taking on H plus. So what it forms is NH4 plus. So the conjugate acid of ammonia is NH4 plus. What is the conjugate base of water? So that means now water is acting as an acid, losing a proton, and what it forms is OH minus. So the conjugate base of water is OH minus. KW, our next section. As we saw before, when we put HCN in water, it acts as an acid. And what it does is it forces H2O to act as a base, to take on that H plus. And we get the products H3O plus CN minus. If, on the other hand, we put ammonia in water, well, this time ammonia is a stronger base than water is as a base, and so it forces this time water to act as an acid. That is, ammonia paired up with water forces water to act as an acid, but HCN paired up with water is a stronger acid than water is an acid, so it forces water to act like a base. Water can act as both an acid or a base. It depends what it's paired up with. Whichever is the stronger of the two, that sets what water will do. Water is that typical one that acts as an acid or a base. It's called amphiprotic, meaning it can act as acid or base. In fact, water does not need another acid or base for an acid-base reaction to occur. It auto-ionizes itself. So here's an example of an auto-ionization reaction. H2O plus H2O, where one acts as an acid, one acts as a base, forms to a very small extent, but nonetheless does form some OH minus plus H3O plus. We can write the equilibrium expression for that reaction, which we call not just K, but KW, W for water. KW equals OH minus times H3O plus, their concentrations. It turns out that at around room temperature, KW is 1.00 times 10 to the minus 14. That's a number that we will be using a lot, so remember it. The product of OH minus times H3O plus always equals 1.00 times 10 to the minus 14 at 25 degrees. Even if the OH minus concentration or the H plus ion concentration are modified by adding an acid or a base. So if we have an acid, we have more H3O plus than OH minus, but the product of the two will still at 25 degrees Celsius equal 1.00 times 10 to the minus 14. So here's a problem. What are the OH minus concentration and H3O plus ion concentration of pure water at 25 degrees Celsius? Always assume 25 degrees even if the problem doesn't state that. Assume 25 degrees unless the problem states otherwise. Alrighty, so we have our ice table. And notice that the OH minus and H3O plus concentration are 0 initially. They change by X, they increase. And we have the 1-to-1 ratio, so they both are X. So at equilibrium, we have X for each. So we have Kw equals OH minus times H3O plus. 1.00 times 10 to the minus 14 equals X squared. X equals 1.00 times 10 to the minus 7. Now X equals the OH minus and the H3O plus ion concentrations. So those concentrations are in pure water at 25 degrees, 1.00 times 10 to the minus 7 molar. And you will see that number a lot. Their concentrations are always equal in pure water. Kw is like Ka if water is acting as an acid, and Kw is like Kb if water is acting as a base. So which acid is stronger, HCl or H2O? So what we do is we think of the Ka for HCl and the Kw for water. Which is the larger? Well, since HCl is a strong acid, its value is basically, its Ka is basically infinity, so Ka is greater than, Ka of HCl is greater than Kw, so HCl is the stronger acid. Which acid is stronger, HCN or H2O? Well, for H2O, Kw is 10 to the minus 14. For HCN, Kw is around 10 to the minus 10. So Ka of HCN is greater than Kw, making HCN the stronger acid of those two. Of course, HCN is still a weak acid. Which base is stronger, ammonia or water? Well, the Kb for ammonia is about 10 to the minus 5, which is much bigger than Kw, so that makes ammonia, NH3, the stronger base. Our next section is pH. We can think of pH as kind of like the power of hydrogen. Mathematically, pH equals the negative log of the H3O plus ion concentration. So if we have the H3O plus ion concentration and we want pH, we use that equation. If, on the other hand, we have pH, but we want the H3O plus ion concentration, then we use the second equation. H3O plus concentration equals 10 to the minus pH. Since we're going to be using logarithms when we're working with pH, let's do a little logarithm review. Log is to the base 10 as the natural log ln is to the base e, where e is like 10, just a number. Its value is 2.71828, and then it goes on from there. So e is just a number. So ln and e go together, log and 10 go together. The log of 100. What is that? Well, what that means is, what is the exponent on 10 that gives 100? The log of 100 is 2 because 10 squared is 100. The ln of 7.39 means, what is the exponent on e that gives 7.39? Well, the ln of 7.39 is 2 because e squared is 7.39. And of course, you know that there's an log key and an ln key on your TI graphing calculator, if that's the type you have. Otherwise, figure out where those keys are on your calculator. What is the pH of pure water? From above, we have the H3O plus ion concentration equal to 1.00 times 10 to the minus 7 molar in pure water at 25 degrees. pH equals negative log of the H3O plus ion concentration. So we have the negative log of 1.00 times 10 to the minus 7. that log of 1 times 10 to the minus 7 is equal to the log of 1, which is 0, plus the log of 10 to the minus 7, which is 10 to the minus 7. And then we change the sign because our equation has negative in it, and we get the pH is 7.000. So that's how we get the pH of pure water being 7. Something else to note is sig fig stuff. So notice that in our number 1.00 times 10 to the minus 7 molar, the sig figs are determined from the 1.00. That number has 3 sig figs in it. The minus 7 is just, you might say, a placeholder. It's showing us how many zeros are in front of the 1. The sig figs are expressed in the pre-exponential factor, the 1.00 part. And sig figs in pH are expressed in the decimals of the pH value. That is, pH of 7 means that comes about from the 7 that's not sig fig related. That 10 to the minus 7 is placeholder stuff, not sig fig stuff. So the 7 in the front of the decimal point is, you might say, coming from placeholder stuff, not sig fig stuff. The 1.00 means we have 3 sig figs in that number, and therefore we show 3 decimals in our pH value. So 1.00 times 10 to the minus 7 has 3 sig figs, so we write the pH value to 3 decimals. What is the pH of 0.010 molar HCl? So what we have is 2 sig figs in that number, so we're going to end up with pH having 2 decimals. Alrighty, now HCl is a strong acid. That means that the H3O plus ion concentration is equal to the original HCl concentration, which is 0.010 molar. So we have then pH equals negative log of H3O plus, pH equals negative log of 0.010. We get the pH is 2.00. What is the pH of 0.10 molar acetic acid? Well, acetic acid is not on the list of strong acids, so it's a weak acid. We look up its Ka value and we find its Ka value is 1.8 times 10 to the minus 5. Since acetic acid is a weak acid, the H3O plus ion concentration is less than the original acid concentration. But we can't calculate pH without having the H3O plus ion concentration. So when we're working with a weak acid, we must either be given the H3O plus ion concentration, or, as we will do later in this chapter, calculate it. Let's say that we're given that in 0.10 molar acetic acid, the H3O plus ion concentration is 0.0013 molar. So we have what we need to finish our calculation. So we take the negative log of 0.0013 and we get that the pH is 2.89. What is the pH of 12.0 molar HCl? So what we have is a very concentrated solution of a strong acid, so we're going to expect a very small pH. 12.0, that's got 3 sig figs, so we'll expect 3 decimals in our pH value if we're properly expressing sig figs. I see that I only have 2 decimals. Okay, so pH is the negative log of the H3O plus ion concentration, so the negative log of 12.0. So we have the pH is negative 1.08. Now, it's negative. So as we talked about before, typically pHs are between about 0 and 14, but they can go below 0 and they can go above 14. So when we have a strong acid and a concentrated solution, we have definitely very low pHs. Our next section is pOH, pKw, pKa, and pKb. In general, px is negative log of x, x being whatever quantity we're referring to. In general, x is 10 to the minus px. Alrighty, well, so if x represents OH, we have pOH is negative log of OH minus concentration. OH minus concentration equals 10 to the minus pOH. pKw, Kw from that of water, is equal to minus log of Kw. We have minus log of 1.00 times 10 to the minus 14, which is 14.000. Kw is 10 to the minus pKw. pKa, so that's a quantity that often biochemists work with. Instead of working with Ka values, biochemists often work with pKa values. pKa is equal to negative log of Ka, or Ka is equal to 10 to the minus pKa. pKb equals 10 to the minus Kb, or Kb equals 10 to the minus pKb. All right, now we'll come up with a pretty handy equation. Kw equals H3O plus times OH minus. If we take the log of both sides, we have the log of Kw equals the log of H3O plus the log of OH minus. If we multiply through by a negative, we have negative log Kw equals negative log of H3O plus minus the log of OH minus. The negative log of Kw is pKw. The negative log of H3O plus is pH. And the negative log of OH minus is pOH. Or we could write pH plus pOH is equal to pKw, which is equal to 14.000. That's a very handy equation because sometimes in a calculation we've calculated pOH, and yet what we really want is pH, so we'll use that equation there. All right, now we will calculate the pH of weak acids. And we will do this problem here. Consider 0.10 molar acetic acid. What is its pH? And something new for us, percent ionization. What is its pKa? Ka equals 1.8 times 10 to the minus 10, times 10 to the minus 5. This is how we calculate the H3O plus ion concentration that we used in that earlier problem. Alrighty, so we have our reaction, HA plus H2O in equilibrium with H3O plus A minus. Our ice table has HA original concentration of 0.10, the other two, 0. HA goes down by negative x, and H3O plus A minus goes up by x. At equilibrium for HA, we have 0.10 minus x, which is about 0.10 due to the smallness of Ka. H3O plus A minus are both x at equilibrium. So we have our Ka expression, H3O plus times A minus over HA. We have 1.8 times 10 to the minus 5 equals x times 0 divided by 0.1, and we would find that x is 0.0013. So we do our check to make sure our approximation is okay. We take x, 0.0013, divide by the HA, 0.10, multiply that all by 100, and we get 1.3%, which is less than 5, so we're okay. According to our table, at equilibrium, the H3O plus concentration is X. So the H3O plus ion concentration is 0.0013 molar. That's that number that we used in that calculation just recently. So the pH is the negative log of that, and we get the pH to be 2.89. Percent ionization. So remember in our problem we had to determine pH, percent ionization, and pKa. So percent ionization, that is the amount of H3O plus that forms as compared to the original HA concentration. So we have percent ionization equals H3O plus concentration over HA initial concentration times 100. We have 0.0013 over 0.10 times 100. We get the percent ionization is 1.3%. Notice that that's also our approximation check. They both are the same. But the percent ionization, what that means for us is how much of that original stuff, or what percent of the original acid dissociates. Well, only 1.3%. That's not very much. If we had, instead of our acid of 0.10 molar, if we had 0.010 molar, so 10th as concentrated, and we went through the same calculation, we would find the percent ionization is 4.2%. So what that ends up meaning to us is, as concentration of the original acid increases, the percent ionization decreases. The more of the original stuff we have, percentage-wise, the less of the products we get. Okay, the last thing that we had to determine was pKa. So that's the negative log of Ka, the negative log of 1.8 times 10 to the minus 5, which turns out to be 4.74. Our next problem is calculate the pH of 0.10 molar aluminum chloride. Well, it's interesting, but aluminum chloride is a bit acidic. Its Ka value is 1.4 times 10 to the minus 5. It's about as acidic as acetic acid is acidic. So when we put that aluminum chloride in water, what it forms is a complex ion. It forms Al surrounded with covalent bonds by 6 water molecules. You see in the diagram below that a lone pair on oxygen of 6 waters forms a covalent bond to Al3+, and that's due to the aluminum being a rather small ion and being highly charged, 3+. Well, being highly charged, the electrons between the O and the Al3+ are being drawn toward the Al3+. Of course, we know negative likes positive. Well, O also likes electrons, being electronegative, so it's pulling the electrons from the hydrogen bond toward itself. And typically, within a complex, only about one H plus ends up separating from the O due to losing its electrons to the O. So what we end up with is H plus in water, and that forms H3O plus. So our reaction, our acid-base reaction, our Ka reaction is AlOH6 3+ plus water in equilibrium with H3O plus AlOH H2O5 2+. So it's a Ka expression, and aluminum is acting as a monoprotic acid, a weak one. So we can write that as that reaction as, in generic terms, HA plus H2O in equilibrium with H3O plus A minus. We fill in our ice table with our original concentration, which was, according to our problem, 0.10 molar. So we run through filling out the ice table, the equilibrium expression, putting our Ka of 1.4 times 10 to the minus 5 equals 2x squared over 0.10. We get that x, which represents the H3O plus ion concentration, is 0.0012 molar. We do our check. We take that 0.0012 divided by 0.10 times 100. We get 1.2%, less than 5%, so we're okay. So now we take the negative log of 0.0012 and we get 2.93 for the pH. So rather acidic. Okay, now we'll look at bases, the pH of strong and weak bases. Calculate the pH of 12 molar NaOH. So NaOH is a strong base, which means OH minus concentration equals the original NaOH concentration. So we know that the OH minus concentration is 12 molar. All right, so POH, because we have OH minus, so we'll calculate POH. That's the negative log of the OH minus, which is negative log of 12, which is negative 1.08. But what we want is pH. So we chemists, we think in terms of pH, not POH. We have a feel for pH. So we want pH. So we use that handy equation we developed earlier, 14.00 equals pH plus POH, or pH equals 14.00 minus POH, 14.00 minus the negative 1.08, and we get that the pH is 15.08. Just as with acids, bases are corrosive, and the larger is the pH value, the more basic, the more corrosive is the solution. In the acid perspective, the smaller is the pH, the more acidic, the more corrosive is the solution. All right, now we'll do a calculation with a weak base. Consider 12 molar NH3, and that's the typical concentration of household ammonia cleaner. What is its pH and percent ionization? What is pKb? And Kb is 1.8 times 10 to the minus 5. So it's a base. Generically, we could write that as B plus H2O in equilibrium with Hb plus OH minus. So we fill in our ice table with our original concentrations, 12, 0, 0. Change, negative x, positive x, positive x. Equilibrium, 12 minus x, or 12, approximately, and then x and x. Kb is Hb plus times OH minus over B, so we have 1.8 times 10 to the minus 5 equals x squared over 12. We calculate x is 0.015. We do our check. 0.015 over 12 times 100 is 0.13%, which is much less than 5%, so we're okay. So we see that x is the OH minus concentration, so we have OH minus concentration equals 0.15 molar, 0.015 molar. So we have OH minus, so we'll calculate POH. That's negative log of OH minus, negative log of 0.015, we get 1.82. But we want pH, so we have pH equals 14.00 minus POH, which is 14.00 minus 1.82, or 12.18. So this value is smaller than that of the 12 molar NaOH because NaOH is a strong acid, so it's more corrosive even though concentration is the same. Next, we want a percent ionization, which is the amount of OH minus divided by the original base concentration times 100. We have 0.015 over 12 times 100, or percent ionization is 0.13%. Lastly, we want the pKb, so that's the negative log of Kb, the negative log of 1.8 times 10 to the minus 5. We get pKb is 4.74. Our next section is polyprotic acids. HA is a monoprotic acid, and we would write that as HA plus water forming H3O plus A minus. Well, polyprotic acids have more than one proton. H2A, H3A, H4A, etc. Those are, in general, polyprotic acids. They can have multiple ionization steps. If we have H2A, its steps would be H2A plus water forming H3O plus HA minus, HA minus plus water forming H3O plus A2 minus. We would have Ka1 for the first step, Ka2 for the second step. So we see that their equilibrium expressions are Ka1 equals H3O plus times HA over H2A, and Ka2 is H3O plus times A2 minus over HA minus. Ka1 is always greater than Ka2 since forming a doubly ionized product is less stable than a singly ionized products. Pretty much sulfuric acid is the only common acid that I can think of that fits this, but for some acids, like sulfuric acid, they're strong acids in the first step. Ka1 is huge, basically infinity, but they are weak in the second step. Okay, so we will keep that in mind as we do this problem. Calculate the pH of 0.10 molar H2SO4. Ka1 is huge, so it's strong in the first step, and Ka2 is 0.012. It's weak in the second step. So we'll calculate the pH from the two steps together. And in our first step, it goes all the way to completion. So if we do our ice table, we would write H2A plus water in equilibrium with H3O plus HA minus. And we have, for the H2A, original 0.010. It changes by that amount because the reaction goes all the way to completion. So the change is 0.010. We have none at equilibrium. For the H3O plus and the HA minus, start at 0, go up by 0.010, and so are 0.010 at equilibrium. Now we do our second step, because that will contribute a little bit to the H3O plus concentration. So our second step is HA minus plus H2O in equilibrium with H3O plus A2 minus. We're starting with HA minus being 0.010 and H3O plus concentration being 0.010. A2 minus is 0. So it's an equilibrium now. So we have minus X, X, and X. At equilibrium, we have 0.010 minus X, HA minus, 0.010 plus X for H3O plus, and then X for the A2 minus. So our Ka2 equals H3O plus times A2 minus divided by HA minus. We have 0.012 equals 0.010 plus X times X over 0.010 minus X. Now, unfortunately, we cannot drop X with respect to the 0.010 since Ka2 is large. I mean, it's it's a number, but it's a big Ka value. That is, the change will be large. It won't be negligible in comparison to the 0.010. If we did try to drop it with respect to 0.010, we would get x equals 0.012, and the check would give us an error of 120%, which is greater than 5, so we can't do that. So we have to go through the full math. So I'll leave that for you to go through. It turns out we get the two roots, one positive, one negative. We drop the negative one. It doesn't make physical sense. Now, in our table here, we have that the H3O plus ion concentration is 0.010 plus X. And so we have, for the H3O plus ion concentration, 0.010 plus 0.00452, or 0.015 molar. We take the negative log of that, and we get the pH is 1.82. So it's a little bit smaller a value than if we had considered only the first ionization step. So we have to consider both steps in the case of sulfuric acid. For most polyprotic acids, it turns out that Ka2 is so small that we don't have to often go to the second step. We just can work with the first step. In carbonic acid, H2CO3, Ka1 is 4.3 times 10 to the minus 7. Ka2 is 5.6 times 10 to the minus 10, so much smaller that it turns out in a calculation of pH, we only have to run through step 1. Let's prove that to ourselves. Let's calculate the pH of 0.010 molar H2CO3. All right, so it's different from the sulfuric acid because both steps with carbonic acid are equilibrium steps. So we go through step 1, we do the ice table, and we calculate what X would be, and that is the H3O plus ion concentration, and it turns out that value is 0.0000656 molar. We do the check, all is okay. Now we run through the second step, another equilibrium value. We put in our initial amounts, our change, run through all the algebra. Luckily, we can do that approximation. We end up getting that X is that incredibly tiny number, all those zeros ending with 5, 6. When we add that incredibly tiny number to our concentration of H3O plus from step 1, we find that it's completely negligible. So the pH is basically that we would have calculated from step 1 alone, 4.18. Our last section is pH of salts. Salts, it turns out, can be acids or bases if they contain ions of weak acids or bases. Well, the most common salt is sodium chloride. It turns out that is not acidic or basic. A solution of NaCl would have a pH of 7 because neither Na plus nor Cl minus act as acids or bases in water. But a solution of NaCN has a pH greater than 7 since it turns out Cn minus acts as a base in water. A solution of NH4Cl has a pH less than 7 since NH4 plus acts as an acid in water. Okay, so we'll see how that all works here. If we're looking at a solution of NaCl, we're going to look at the sodium ions and the chloride ions, and we're going to think about what is their acid or their base. So the acid of Cl minus is HCl. That's a strong acid. When that is in water, it forms completely H3O plus Cl minus. The Cl minus is a very, very weak base. It basically is not a base at all. So when we put Cl minus in water, it does not want to go back to HCl. It just floats around in the water, not affecting the pH. It does not grab H plus from water. The Na plus, its base would be NaOH. That's a strong base. It completely forms in water OH minus and Na plus. The Na plus does in no way want to connect with the OH minus. So when we have Na plus in water, we get no reaction. It just floats around. So that means a solution of NaCl is neutral, has a pH of 7. But a solution of NaCN, well, the Na plus does nothing, as we've talked about, but the Cn minus is the conjugate of the weak acid HCN. Being a weak acid, it does not readily form Cn minus. It does a little bit in water, but not very much. Cn minus is a weak base. That is because HCN kind of likes being together. Cn minus, to some extent in water, acts as a base, taking an H plus from water, forming OH minus plus HCN. Well, the fact that there's OH minus there means that solution will have a pH greater than 7. If we have a solution of ammonium chloride, NH4Cl, the ammonium ion is the conjugate acid of the weak base ammonia. When we put that weak base ammonia in water, we get it acting as a base to a small extent, taking an OH minus from, an H plus from water to give us OH minus plus NH4 plus. So that NH4 plus, it's a weak acid, it's a stronger acid than water. So when we put it in water, it's going to a small extent, act as an acid, giving up a proton to water, and therefore we end up with H3O plus to a small extent, which makes the pH less than 7. Alrighty, so using that information, we will calculate the pH of 0.15 molar NaCN, which we've talked about. Its pH is greater than 7 due to the Cn minus. What we're given is the Ka of HCN to be 6.2 times 10 to the minus 10. So the Cn in water, Cn minus in water, acts as a bit of a base. And it takes an H plus from water to give OH minus. So there we have Cn minus plus H2O in equilibrium with OH minus plus HCN. We have a Kb kind of reaction that we have to work with. Now, we're given Ka in our problem, so maybe we would try to find the Kb of Cn minus in a table. So if we find it, great. But if we don't find it, then we can calculate it from Kw equals Ka times Kb. That is, Cn minus and HCN are conjugates of each other. Well, it turns out that of those two, the one acting as an acid, the other as a base, their Ka times Kb product always equals Kw. This equation always works for a conjugate acid-base pair. So to find the Kb for that reaction, we have Kb equals Kw over Ka. Kb equals 1 times 10 to the minus 14 over 6.2 times 10 to the minus 10. We get that Kb is 1.6 times 10 to the minus 5. And we fill in our ice table with the original concentration, which was 0.10 molar for the Cn minus. We run through the table and we get X is 0.0016. We do our check, it's less than 5%. So we have the OH minus concentration is 0.0016 molar. We take the negative log of that and we get POH is 2.80. We calculate the pH from pH equals 14.00 minus POH. 14.00 minus 2.80, the pH is 11.20, so significantly greater than 7. Here's a calculation with ammonium chloride. So we have 0.15 molar ammonium chloride. We're given the Kb of ammonia to be 1.8 times 10 to the minus 5. Now, when we write out the reaction of NH4 plus in water, we get NH4 plus water in equilibrium with H3O plus NH3. That's a Ka kind of expression. We have to calculate Ka. So Ka equals Kw over Kb. Kw 10 to the minus 14, Kb 1.8 times 10 to the minus 5. We get that Ka is 5.6 times 10 to the minus 10. So we fill in the ice table, our equilibrium expression Ka, we put in our numbers. We find X is 9.1 times 10 to the minus 6. We do our check and we find that we're less than 5%, so we're okay. So the H3O plus ion concentration is 9.1 times 10 to the minus 6 molar. We take the negative log of that and we get that the pH is 5.04, definitely less than 7. Now, the one thing that is on this page here that we didn't go over is the proof of why Kw equals Ka times Kb. So we have HA plus H2O in equilibrium with A minus plus H3O plus. And then that would be the Ka expression. The corresponding Kb expression for the conjugate base A minus is A minus plus H2O in equilibrium with HA plus OH minus. So those are the two Ka and Kb reactions with HA and A minus being conjugates. If we write out what Ka is and multiply it by what Kb is, we have Ka times Kb is A minus times H3O plus over HA. That would be the Ka part. The Kb part is HA times OH minus over A minus. Now we see that we have A minus over A minus, that's gone. We have HA over HA, that's gone. And we end up with just H3O plus times OH minus, which is, as we know, Kw. So that's the proof of why Kw equals Ka times Kb for a conjugate acid-base pair. So with that, we have finished chapter 14, the video. So as always, go back through it slowly as it helps you. Do all the problems in the handout on your own at your own pace. Read chapter 14 in the textbook and do the assigned homework problems.